So we'll do problems on chapter 2. We have a gas is compressed from V1 equals to 0.3 meter cube at a pressure of 1 bar to V2 equals to 0.1 meter cube at a pressure P2 of 3 bar. Pressure and volume are related in a linear way during the process for the gas. Find the work in kilojoule. So if you remember, we already said the general equation of work is equal to integral PdV. And we have several particular cases in which we can simplify the calculation instead of doing integration. The first case is when P is constant, we just say then the work is equal to P delta V. And we said also another particular case is when pressure is varying in a linear way with volume. Then what can we say when P is linear? How we can calculate the work?
نلاقي الاريا
فينا نلاقي الاريا هيدي one method yes وفينا نستعمل دغري P average times delta V. إذا بدنا نشتغل على الاريا all we have to do is to draw a small graph. Okay, if you draw a small graph you have linear variation of pressure with volume, and we know that integral PdV represents the area under the graph. And since you have a trapezoidal area, okay, you can say that we know the coordinates here. You have this is P1. Let's say P1, V1. Here I'm drawing any line not related to this problem, okay? Because I'm talking about a general linear process. So P2, V2. And then you can say that the area of a trapezoid is equal to the average base times the height. And the average base is equal to, you can calculate it as P1 plus P2 over 2. So from area of trapezoid, the corresponding area will be P1 plus P2 over 2 times delta V. So if you multiply by delta V, you get the area of the trapezoid. So that's why whenever you have a linear process, you can directly apply that W is P1 plus P2 over 2 times delta V, which is V2 minus V1. Now just we should pay attention for units, okay? So if we put P here, since we need P work in kilojoule, if you need work in kilojoule, you can put P in kilopascal and delta V in meter cube. Okay, and we know that 1 bar is 10 to the power 5 Pascal. So we can write it as 10 to the power 2 kilopascal. So it is just then a replacement in the formula to find the value of the work. Okay, now since your volume is decreasing, so V1 is 0.3, V2 is 0.1, then you will get a negative work. And this means that we are putting work on the system. Okay, any question on this problem? So here you have the detailed solution. Another problem, a 2 centimeter diameter surface at 1000 Kelvin emits thermal radiation at a rate of 15 watt. What is the emissivity of the surface? Assuming constant emissivity, plot the rate of radiant emission in watt for different surfaces temperatures. The Stephen-Boltzmann constant is given to be equal to 5.67 times 10 to the power minus 8 watt per meter square Kelvin 4. So here, this is a problem about radiation. So we need to use the formula of radiation. We know that Q radiation in watt, okay, is equal to the emissivity epsilon times sigma, which is the Boltzmann constant, times the area, which is emitting the radiation heat, times T surface to the power 4. And epsilon is without unit. Sigma is given, and the unit is watt per meter square, Kelvin 4. The area is in meters square, and the temperature is in Kelvin. In this problem, we have everything except epsilon. Sigma is given. The area, we can find it because we have a circular surface. So this will give us an area of pi d squared over 4. Just pay attention to convert the diameter from centimeter to meter. So when you replace here, diameter is 0.02 meters. Okay.
فينا كمان نعمل باي ار سكوير.
أكيد. Okay. So then you can find the value of epsilon. And once you get epsilon, then you can find the flux of radiation for different temperatures. And if you plot the figure as expected, you have, because it's proportional to T to the power 4, as the temperature increases, the slope will increase. So you can see here how the radiation flux increase in a high rate with temperature, because the radiation flux is proportional to T to the power 4. Okay. Any question on this? Okay. Another problem. A gas is contained in a closed rigid tank. An electric resistor in the tank transfers energy to the gas at a constant rate of 1000 watt. Heat transfer between the gas and the surroundings occurs at a rate Q dot equal to minus 50 times T, where Q dot is in watt and T is time here in minutes. Okay. We want to plot the time rate of change of energy of the gas for T between 0 and 20 minutes in watt. Okay, so first, whenever we have such a problem, the first step will be to write the energy balance. And we start from the energy balance to solve our problem, okay? From the energy balance, what can we write? Any variation in energy can be calculated as Q dot minus W dot. This is the rate equation, okay? Because here we are finding the variation with time. So as the problem stated here, we have just two sources of change in energy. The resistor is here, so we have production of energy, and we have heat loss to the surrounding equal to minus 50 T. Okay, so we don't have any work exchange with the surrounding. That's why W dot is 0. So we can write that dE by dt is plus 1000 because it's a generation term. Okay, so it's adding to the system, and minus 50T because we are losing heat to the surrounding. And the convention for heat, we know that we put here plus Q dot because everything coming in is accounted as positive and everything getting out is accounted as negative. So this is our equation. And because they told us, when they gave us Q surrounding function of time, they told us that the unit here, T is in minute, okay? So because T is in minute, because 50 is in watt per minute, T should be in minute, okay? Because you have this, you have the units of these equations. For dE by dt, it should be in watt, okay? Since here whenever they gave us the equations, they told us that T is in a minute. So 50 should have the unit of watt per minute. Then when we do minus 50T, we get the unit of watt. Okay. So as we can see, the energy is decreasing in a linear way with time. And we can represent its variation by graphically by just drawing the line. They asked here to represent the variation from 0 to 20 minutes. So all you have to do is to plot from 0 to 20 minutes the straight line. Okay. Now, they are asking also to determine the net change in energy of the gas after 20 minutes. So we want to find delta E. We want to find delta E after 20 minutes. Like here we have several possibilities. Okay, so this is dE by dt. We can say that the change, we can do it graphically if you want. Okay, or we can do it by calculation. So here, if we want to do it by calculation to find delta E, all we have to do is integration, because this is a differential equation. We can do separation of variables. So we can write that dE is equal to minus 50T plus 1000 dt. And now we integrate. We are interested to find the variation of energy between 0 and 20 minutes. So from 0 to 20. And here we integrate. When we do the integral of dE, we'll get delta E. Okay, so delta E between 0 and 20 minutes is equal to minus 25T squared plus 1000T between 0 and 20. So this is the analytical method to find the variation in energy. Okay, and delta E will be in watt. So if they ask for it in kilowatt, all we have to do is to divide by 10 to the power 3. Now, what is the second method? What can we do? What is the second method to find delta E? You can use the graphical method. Okay, in the graphical method, delta E will represent the area. So here, when you want to integrate a function, okay, you know that if you have, for example, if you have v, let's say, function of time as a graph, okay, in dynamics, when you have v function of time and you want to find the displacement delta s, you can say it's since v is ds by dt, I can just consider the area under V graph to find the displacement delta S. Same concept here, okay? Here you have dE by dt function of time. So you can say that the area under this line will correspond to the variation in energy, okay? And since it's a triangle, you can easily calculate the area. So it's equal, it's 1000. So it's 1000 times 20 over 2. Okay, and this value will be the value that you got okay, will be in joule, because this is in watt, this is, no, pay attention, it will not be in joule. Why? Because here, when you did the integration, the unit you obtain is watt minute, okay? And joule is watt second. So if you want to convert it to joule, you should say that 1 minute correspond to 60 seconds. Okay, so you should multiply the result by 60 to get it in joule. And if you want it in kilojoule, you then divide by 10 to the power 3. So just pay attention for units here, okay? If T was in second, you can directly say the result is in joule. It's because T is in minute, the result you get is watt times minute. And 1 minute is 60 seconds, so you should do some conversions to get the final unit in joule. They also asked you if electricity is valued at $0.08 per kilowatt hour, what is the cost of the electrical input to the resistor for 20 minutes of operation? So here we want to determine what is the electricity cost in this case. The electricity cost is due to what? The generation, because the flux that is coming from the resistor, okay? You have your resistor is providing energy at 1000 watt, okay? And if you operate it for 20 minutes, what will be the amount? Because it's a constant here, the resistor power is constant. So if you want to determine the amount of energy it will give you during 20 minutes, what should you do then? What should we do here? Yalla, who can tell me? What should we do to find the energy transfer if we have the power and the time?
ولازم نضربهم
Yes,
بالوقت.
yes, exactly. So this is a constant, okay? You can say that the energy delta E that is coming from the resistor is equal to the power, which is constant here, times delta T. And also here we should pay attention for units. So the power is in watt, so 1000 watt, times delta T, which is in minute, 20 minutes. We get the result in watt minute. Okay, now the cost is given per kilowatt hour. So you know the cost per kilowatt hour of electricity. That's why you should convert this result to kilowatt hour. Okay.
يعني بقى نحول 20 minutes ل hours.
مظبوط، يعني أول شيء بدنا نحول 20 minutes ل hour، يعني we should divide by 60. Okay. Concerning to get in kilowatt hour, we have in watt. To get in kilowatt hour, we should divide by 1000. Okay, so in total, we should divide this result by 60 first, then by 1000 in order to get the result in kilowatt hour. And then once we get the result in kilowatt hour, to determine the total cost, we just multiply the price per kilowatt hour by the number of kilowatt hour, and then we can get the cost of electricity. Okay. Any question on this? So we are done with this problem. Another problem. Air is contained within a piston cylinder system and is slowly heated. As shown in the figure, during this process, the pressure first varies in a linear way without volume, varies in a linear way with volume, and then remains constant. Determines the total work in kilojoule. So here also, it's a simple problem. We have two phases of pressure variation, one that is linear, one that is constant. And we want to find the total work. So we can do it graphically here. We can say we have P function of V. So the work is equal to the area under the graph. And we can divide this area into two parts. From 1 to 2, you have a linear process. So you have to take into consideration the area of the trapezoid. And from 2 to 3, you have a constant pressure. So you just have the area of a rectangle. And all you have to do then is to add area 1 to area 2. And what will be our unit? Since P is in kilopascal, so when you do integral PdV, you will get the result in kilowatt. Now, as a value for area 1, to compute area 1, it's the average base as we said. So you have the pressure here, P1 is 100, P2 is 150. So just you have to apply P1 plus P2 over 2, which is here 125. So this will give you 125 times delta V. Delta V is 0.045 minus 0.03. So it's equal to 0.015 meter cube. Then you will be done with the first term. And for the second part, you have a rectangle. So you have P constant. So it's just plus 150 times delta V of phase 2. Delta V of phase 2 is 0.07 minus 0.045. So you multiply by 0.025. And then you get directly your total work in kilojoule. Sorry, you get first your power in kilowatt. Okay, so here it's a, yes, yeah, you have kilopascal, sorry, مش kilowatt, kilojoule, because you have here in pascal and meter cube. Okay, so when you multiply, you directly get your result in kilojoule. If they give you, let's say, the amount, the time, okay, you can find the average power. So if they give you the total time of this process, you can calculate the average power as delta E over delta T, and then kilojoule over second, let's say, will give you the value in kilowatt. Okay, another problem. The outer surface of the grill hood shown in the figure is at 47 degrees, and the emissivity of this surface is 0.93. The heat transfer coefficient for convection between the hood and the surroundings at 27 degrees is 10 watt per meter square Kelvin. Determine the net rate of heat transfer between the grill hood and the surroundings by convection and radiation in kilowatt per meter square of surface area. So here we have a heat transfer process between the surface and the surrounding, okay? And we have already seen that we have several ways of heat transfer between a surface and its surroundings. So you can have first, because of flow motion, you can have heat transfer by convection. And since you have surroundings at a certain temperature, you can have also heat flux by radiation. Okay, so first we know that Q convection is given by the following formula, is equal to HA delta T. Now, they want the result in kilowatt per meter square. Because they want it in per unit area, you don't multiply by A. So they are asking for Q second. Okay. And since here we want it in kilowatt, so we should pay attention for units. Okay. So first we can find it in watt, then we divide by 10 to the power 3. To get it in watt, they already gave us the convective coefficient in watt per meter square Kelvin. So we just have to replace H by 10. For delta T, as I told you, delta T in degrees and delta T in Kelvin is the same. So just you have to do the difference of T surface minus T ambient or T of air, which is here T0. Okay, so you have TS is 47 and T0 is 27. So this is for the convective flux. Now, for radiation, okay, for radiation, we can also consider that since they gave us just, if you want, here, you have the surface temperature is given, okay? And we know that heat loss by radiation from a surface, so Q radiation, is equal to epsilon, because they wanted per unit area, I will not multiply by A. So it's epsilon times sigma times T surface to the power 4. Okay, so this is emitted flux by radiation. Now, in case you have an enclosure, for example, you can have heat that is received by the surface by radiation, should account for the net flux. So let's say you have an enclosure, you should do here Q net is epsilon sigma TS4 minus T enclosure to the power 4. Why minus? Because this one is received by the surface. And to find the net emission, so you will do the emitted flux minus the received flux. But here, since they didn't tell us that we have any surfaces surrounding the system, so we can consider that we just have emission from the surface. Okay. Here, all if you want, they should be more specific. They should tell you that the walls, or this enclosure has walls of surface temperature equal to the air. Then you can do minus T0 to the power 4 as I did here. So the given should be clearer, okay, to tell you that you are in a room, let's say, and they just give you T0. So you can assume that the walls temperature are equal to T0. In the exam, of course, this will be clear for you, okay? And then you can determine in total the net loss from the surface towards the surrounding as the summation as the convective flux plus the radiation flux. Another problem, as shown in the following figure, the outer surface of a transistor is cooled convectively by a fan-induced flow of air at a temperature of 25 degrees and a pressure of 1 atmosphere. The transistor's outer surface area is 5 times 10 to the power minus 4 meters squared. At steady state, the electrical power to the transistor is 3 watt. Negligible heat transfer occurs through the base of the transistor. The convective heat transfer coefficient is 1000 watt per meter square Kelvin. Determine first the rate of heat transfer between the transistor and the air in watt and the temperature at the transistor's outer surface. Okay, so here what we want to do is to find, if you want, first, what is the rate of heat transfer between the two, the surface, the solid and the fluid, and then to calculate the temperature at the transistor outer surface. So here we should do an energy balance for the transistor. Whenever they say we have steady state operation, this means that we don't have change of temperature with time. Okay, so when we write the equation, we are, in general, we write dE by dt equals to Q dot minus W dot. Okay, now whenever they say steady state, this means dE by dt is 0. And as you can see here, the transfer with the surrounding is in terms of heat. Okay, you don't have any work here. You have an electrical power, so you have Q dot generation. So this should be divided into Q dot generation, which is given to the system, to the transistor, and air will take heat out of your transistor. So it's a negative flux. So minus Q dot convection equals to 0. So the equation governing heat here, the heat transfer, is just Q dot generation should be equal to Q dot of convection. Okay, and we know that in this problem, they told us that the electrical power due to the transistor is 3 watt. So we know that this is equal to 3 watt. And we should express in watt now the convected flux, which is H times A times T surface minus T infinity okay. In this equation, we have everything except the surface temperature. H is given, it's 100 watt per meter square Kelvin. The area is 5 times 10 to the power minus 4. The surrounding temperature, T infinity, is 25 degrees. So the only unknown is TS. We can find TS, and the unit of TS, if you replace T infinity in degrees, TS will be in degrees. If you replace T infinity in Kelvin, TS will be in Kelvin. So as we mentioned before, for delta T, you can put it in degrees or Kelvin. It doesn't matter. Any question on this? Okay. Another problem. As shown in the following figure, a gas within a piston cylinder assembly undergoes a thermodynamic cycle consisting of 3 processes in series. We have first a compression with U2 equal to U1. In process from 2 to 3, we have a constant volume cooling to P3 equal to 140 kilopascal at V3 equal to 0.028 meter cube. And in process from 3 to 1, we have a constant pressure expansion with W31 equals to 10.5 kilojoule. For the cycle, we have that W cycle is minus 3.8 kilojoule, and there are no changes in kinetic or potential energy. We want to determine the volume at state 1, the work and heat transfer for process 1, 2 in kilojoule, and we want to determine if this cycle is a power cycle or a refrigeration cycle with explication. So first, whenever we have such problems, it's a closed system, okay? Whenever you have a closed system, you can directly write first that delta E is equal to 0. And
دكتور
this, yes.
بعد 2 minutes بيخلص
Yeah, I will
الميتنج.
start another one, same link, okay? Yeah, I will do it now.